All right, our next topic, Lewis dot structures. There are some stuff that you definitely need to know, so let's go over it. All right, so here we're drawing Lewis electron dot diagrams. It can be asked with or without the word Lewis, and instead of diagram, it could say structure, but it's going to say something about electrons dots, and then a structure or a diagram. So here we go first, where we have to draw one for an atom of iodine. So I have the notation from the periodic table here. What I need is valence electrons, okay? And I'm going to start with the symbol for the element in the center. And then I need to draw only dots for the valence electrons. So I need 7 dots. What I'm going to do is imagine. So I'm going to make this off to the side here because I do not want to draw it like this. I'm going to imagine that the I is in a box like it is on the periodic table. And the dots have to touch the edge of the box. So you can see the dots have to go around like this. Okay. I do not want to stack dots like this. No. Okay. So let's do this. What I'm going to do though is just increase the thickness a little bit so I can do this without, I can do it a little clearer anyway. All right, so ready? I need 7 dots. So I'm going to do it like this. 1, 2, 3, 4, 5, 6, 7. All right, that's it. Now, I could have started somewhere else as long as I have one singular one over here. All right, now I'm just going to give you a little note here that paired electrons will not bond. Unpaired electrons will bond. So iodine, can form one bond. It has one singular unpaired electron. All right, now let's go to ion of iodine. So let's use the same element, right? But now it is ion, all right? So what does that mean? Well, I'm going to look right here. What is the charge of an iodine ion? An iodide ion is -1. But that makes sense. Look, the goal of every atom is to have a complete outer shell. For most, that's an octet or 8. Right now, iodine has 7. So it has 2 choices. It could literally gain 1 or lose 7. Lose 7 is exhausting. So it's going to gain 1. So what will it look like? Well, still the same symbol, right? And let's switch colors for the electrons. So we have 7, 1, 2, 3, 4, 5, 6, 7 to start. It gains 1. But I need to find a way to show that this is not an atom, it's the ion. So what I do is I put it in brackets and I put the charge outside. So 1, negative, or just negative. Okay, so let's see how that applies to magnesium. So symbol, valence electrons. Boop, boop. Now with magnesium, with the first 2 valence electrons, you can pair them together. So you will see them like this a lot, and that's okay. I personally like to do it this way right here because it still shows the unpaired in terms of bonding and the paired for bonding. Okay, but both of these answers would be accepted. All right, so just in case you see it this way, you understand. All right, so what about an ion, right? So same symbol, right? Look here, charge is +2. So let's go through again. Remember, an atom wants to have, in most cases, 8, right? So what happens in this case is magnesium had to gain 6. Ugh, exhausting. Or it could lose 2. That's easier. It will lose 2. So here's magnesium with its 2 valence electrons lost. No dots. So how do I show that this is not just the symbol for magnesium, that it's the ion? Well, I put it in brackets and I put the charge. Okay. So something that you should note here is iodine as an atom has 1, 2, 3, 4, 5 energy levels. As an ion, it also has 5 energy levels, okay? But it has an 8 here at this last energy level, okay? So this ion is bigger than the atom. Why? Because the atom gained electrons. The ion did not gain electrons. The atom did. All right, but now when we look at magnesium, the atom has 1, 2, 3 energy levels, but it lost these 2. So the ion only has 2 energy levels. Notice the last one is an 8, right? So this ion is smaller, not only because it lost electrons, but it literally lost a whole energy level, okay? So in the case of magnesium, the ion is smaller. The atom is larger. Why? Because the atom lost electrons, all right? So that was a lot, and some of it was extra, but it's important to just kind of cover that information as well. All right, so in order to determine bond type, like most polar, least polar, what kind of bond is present, you are going to need electronegativity. All right, so let's go to table S and electronegativity. We can see this column right here. All right. So what is the bond type here? Well, look at the atoms that are connected. It's an H to a Br. So H is 2.2. Br, I have to go scroll down a little bit, right? 3.0. Subtract those numbers. What do you get? 0.8, which puts it in here, polar. Na and Cl. All right, so Cl right here, 3.2. And then Na is 0.9. What do I get when I subtract those? 2.3. So I can just do, it doesn't matter what order, just always go biggest minus smallest. And that puts it here, so ionic. CH4. Now, I don't want to do 4 literal subtractions. So this means a carbon to a hydrogen, a carbon to a different hydrogen, a carbon to a different hydrogen, a carbon to a different hydrogen. So I just need C and H. Okay, H I already know is 2.2. So let's look up carbon, 2.6. That is 0.4. That's right here on this border. So it is weakly polar. Sometimes it is considered non-polar. All right. And then CO2. So we have C, 2.6. And what is O? 3.4. And when you subtract those, what do you get? 0.8 again, which makes polar. So that is how you do bond type. And if this question said, which of the following is most polar, you'd pick the biggest number. I don't care anything else, just pick the biggest number. If it said, which is the least polar, you pick the smallest number. That's just how it rolls. Do it that way. Okay. Now, once you determine whether bonds are polar or non-polar, right? Then we could talk about molecules being polar and non-polar. Polar molecules have no symmetry. So that means the charge is unequally distributed, whereas non-polar molecules have symmetry. So the charge is equally distributed. Okay, so what do I mean? Well, here between H and Cl, I have a polar bond. It's shown this way because this side is partially negative and this is partially positive. So the negative is being pulled this way. Is there anything pulling it in the opposite direction? Nope, polar. Okay, for nitrogen, these are all individual polar covalent bonds. And you see how nitrogen is more electronegative. So nitrogen is partially negative. All of these hydrogen ends are partially positive. So all of it is being pulled this way. Is anything pulling in the opposite direction? Nope, it's polar. Okay, this one, I have some non-polar bonds right here. Okay, but then I have one that is pulling in this direction, so this is partially negative. And is there anything pulling in the opposite direction? No, polar. So that's symmetry. Here, these are polar bonds. So do you see they're being pulled this way? This is partially negative, but you see how one is pulling this way? Boom, one is this way, one is this way. So it's like a tug of war where the boron is being pulled in equal directions. So this ends up being a non-polar molecule with polar bonds. Same concept here, okay? Polar bonds, non-polar molecule. Now, tip is, I'm just going to say this, if all the bonds are non-polar, the molecule is non-polar. The only reason that a molecule could be polar is if it had some polar bonds, all right? So let's just investigate this. All right, draw a Lewis electron dot diagram, identify the molecule as polar or non. All right, oxygen. So we are drawing Lewis dot, right? Valence electrons. So oxygen, 6, 1, 2, 3, 4, 5, 6. Second oxygen, 1, 2, 3, 4, 5, 6. All right. So what I like to do is take, especially when there's just two things, write the two things next to each other, draw a line in between them. That line connects them and uses an unpaired electron attached to an unpaired electron. It's just a neater line here. Now check my Lewis dot structures for the atoms. Are all of the unpaired electrons accounted for? No, they are not. So what I need to do is bond this one also to this one. So a second line. Now I check again. Are all the unpaired electrons accounted for? Yes, they are. But put those remaining paired electrons that don't bond here. All right, so if we talk about this here, so between the oxygen atoms, 4 electrons are shared, or 2 pairs of electrons are shared, or it is a double bond, a double covalent bond. Now, I don't even need to look up oxygen to determine the polarity of the bond, because whatever oxygen is, the other oxygen also is. So when I subtract them, what am I going to get? Come on, 0, right? So it is non-polar covalent bonds. And since all of the bonds are non-polar, it is a non-polar molecule. Also, this, just an aside, is one of the diatomic elements. What are the diatomic elements? Brinkelhoff, right? Ing, Kohl, Hoff. Okay? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. They all exist as diatomic molecules. Okay, so this is a remember situation. All right, let's try the next one, iodine. Okay, iodine right here, 7 valence electrons. We drew this one before. So iodine, 1, 2, 3, 4, 5, 6, 7. And how many iodines do we have in an iodine molecule? 2. 1, 2, 3, 4, 5, 6, 7. So what I'm going to do when I have two, again, I like to do this, take one, connect it by a bond to a second one. That accounts for unpaired electron bonded to unpaired electrons. Anything else unpaired? Nope. Just add the dots that are left and do not leave them out. And just like oxygen, it is a non-polar bond and a non-polar molecule. Okay. All right. Let's do this one. All right. So ammonia. What if you forget what ammonia's formula is? Well, I'm going to show you where in the reference table you can get some help. Okay. Right here. Ammonia. Look at, there it is. NH3. Okay, so it's NH3. Let's draw the Lewis dot. For nitrogen, 5 valence electrons. 1, 2, 3, 4, 5. Hydrogen, 1 valence electron. So I have a hydrogen and another hydrogen and another hydrogen. Okay, so this time it's not one bond. So what I'm going to do is draw the thing in the middle that has the most unpaired electrons. So that's nitrogen. Okay. And I have an unpaired one right here, right on this side. So what I'm going to do is draw a line. And what could I connect? Ooh, a hydrogen. So this accounts for that. All right, this unpaired electron right here. Okay, draw a line and connect it to, guess what? A hydrogen. This unpaired electron, draw a line, connect it to, guess what? A hydrogen. Is that all of the unpaired ones? Yes, it is. Don't forget to add this, those paired electrons that don't bond. Now, when we are determining this polar or non-polar, let's figure out the bond, okay? So for nitrogen, right? Let's see. Oops. Nitrogen's electronegativity 3, hydrogen 2.2. So subtracting it is 0.8, which means the bond is polar. And nitrogen is more electronegative. So that means, so I'm just going to switch color and go a little smaller. That means the polar covalent bond is pulling this way and pulling this way and pulling this way. Is there anything available to pull in the opposite direction for any of that? Nope. So what is this? Polar covalent bonds, polar molecule. Okay. All right. What about water? All right. Well, water's, you should know formula, right? H2O. And hydrogen, 1 valence electron. Boop. Hydrogen, 2 of them. Oxygen, 6, 1, 2. Okay, like this. Well, I have more than 2 things. So I'm going to draw the one that has more unpaired first. Okay. Then I have an unpaired one right here. So on this side, I'm going to draw a line and I'm going to connect it to something else that has an unpaired electron. Go back to my oxygen. I have an unpaired one here. Draw a line and I'm going to, that's going to connect to what else I have available, which is a hydrogen. All of the unpaired are accounted for, so just add these. Now to determine bond type. Well, hydrogen is 2.2. Oxygen is 3.4. Oh, that's definitely polar. All right, so let's draw this one. And oxygen is more electronegative, so it gets pulled this way. Also this way in this bond. Is there anything available to pull in the opposite direction? No, there's not. So again, polar covalent bonds, polar molecule. No symmetry, electrons unevenly distributed in terms of charge. Okay. All right, so this one, carbon dioxide. You know the formula for carbon dioxide, I hope, CO2. All right, so let's draw this one. Carbon, 4 valence electrons. 1, 2, 3, 4. Oxygen has 6, right? 1, 2, 3, 4, 5, 6, and another one. 1, 2, 3, 4, 5, 6. Okay, so this one, a little bit weird. So first of all, which one has more unpaired? Carbon. So I definitely put that one in the center. Okay. Now you can see carbon has unpaired all the way around. So in this case, and maybe this is just something that you have to remember for this molecule in case you have to draw it, but I'm going to divide and put them evenly, one on one side and one on the other side. Okay. So when I do that, I take this unpaired, right, and attach it to this one, okay, here. And then I'm going to do this one to here. But I still have unpaired with carbon, right? So this one is going to also bond here. And this one bond here. That accounts for all the unpaired, but then I have these for oxygen. Let's determine the kind of bond. Carbon 2.6, oxygen 3.4. That shows polar, but this is where you had to remember how to draw it, right? So just remember carbon dioxide looks like this. The polarity gets pulled toward oxygen. So these ends are partially negative over here. But so is there an opposing force to the charge? Yes. So this is unusual. Okay, so first of all, I do see double bonds, right? So that means they are covalent bonds. How else could I describe them? Polar covalent bonds. But because there is symmetry, because the electron charge is distributed equally, it is a non-polar molecule. You definitely should remember carbon dioxide, okay? All right, over here, methane. So methane, you could look at table P and table Q to help you, but it is CH4, okay? So carbon, we know, is 1, 2, 3, 4. Hydrogen, like this, 1, 2, 3, 4. Draw the one with the most unpaired in the center, okay? And then take this, I'm gonna do this one first, that unpaired, and connect it to what? A hydrogen. So this one. This unpaired, connect it to another unpaired, that hydrogen. This unpaired, and finally, this unpaired right here. So this bond, right, 2.6 minus 2.2 is non-polar or very, very low in polarity. But even, it doesn't even matter. Why? Because look at the distribution. It would be being pulled this way, and this way, and this way, and this way, which is symmetrical. So if you have this is called the tetrahedral shape. If you have a tetrahedral shape and all of the atoms connected are the same, that it's a nonpolar molecule. So nonpolar molecule here. All right, nitrogen molecule. All right, so let's try it for nitrogen. 5 valence electrons. What does a molecule mean? Well, it's one of the diatomic ones, right? So it's 2 nitrogens. It didn't say atom, right? So it's only 2 things. So you start by just drawing them together like this. That accounts for this. Another bond accounts for this. Another bond accounts for this. Finally, all done, but they have this. All right. And just like oxygen molecule, just like iodine molecule, non-polar bonds. And if they're all non-polar bonds, it is a non-polar molecule, period. All right, H and Cl. So H1, well, if you forgot hydrochloric acid, please look at table K, and you could see the formula, which is HCl. All right, and then Cl has 7. 1, 2, 3, 4, 5, 6, 7. Okay, only 2 things. Start by literally just draw them with a line connected. All right, that accounts for this. Any more unpaired? Nope. Do this. Okay, H and Cl. So H 2.2, Cl 3.2. So what do I have here? Polar bond, polar covalent. And I only have one bond. So if the only bond is polar, then the molecule is polar. Okay. And one more, bromo-methane. So this, you would look at table R and determine bromo is Br. Meth from table P means 1 carbon. Ane from table Q means all single bonds. Okay. So let's draw bromine. Is 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Carbon 4. 1, 2, 3, 4. Hydrogen has 1. Now, how many hydrogens do I need? Well, if you don't know, just let's see what happens. All right. Which one do I put in the center? Carbon for sure, right? Let's use this one. Right, and to draw a line to one of the things that I have available. Okay, I'll just use the Br to get that out of the way. All right, let's go here, draw a line up. What do I have available? A hydrogen. Well, I still have these 2, which means guess what I have? More hydrogens, right? Methane normally has 4, but since the bromine is taking the place, I'm going to have less. So let's do this one. And is connected here to a hydrogen. Let's do this one. Connected here to a hydrogen. Okay, so remember non-polar bond, non-polar bond, non-polar bond. Oh no, polar bond. Why? Carbon 2.6. What's Br? 30.0. It's going to be slightly polar, but it's different, right? So does this have symmetry? No, it does not. It's only got 1 Br, right? So it's going to be a polar molecule. All right. And that's it. Hopefully that is a great summary for a Lewis dot structure.